Watch out for the cable.
Thank you. Hi, everyone. So I'm Rebecca Wright, Chair of Computer Science at Barnard. We are very happy to have for our computer science seminar today, Niall Williams, who's joining us from NYU, where he is a faculty fellow. His research is very multidisciplinary, addressing computer graphics and applied visual perception. He will talk to us today about several aspects of that work. He completed his bachelor's degree in computer science at Davidson College and his master's and PhD in computer science at the University of Maryland. And he has also interned at both Meta and NVIDIA and has received multiple Best Paper honorable mentions for his research on locomotion in virtual reality. Niall, the floor is yours.
Thank you very much. Really happy to be here. Thanks to everyone who showed up, either on Zoom or in person. And yes, like Rebecca mentioned, I'm going to talk about graphics and applied perception. And so I guess we'll just jump right into talking about the art of optimizing graphics for better user experiences. So first, though, a little bit. Okay, here we go. First, a little bit about myself. So who am I? I'm Niall. If you forget how to pronounce my name, it's the same as the river, just spelled differently. And I originally come from Jamaica. That's where I was born and raised. And then I moved to the US for schooling. So I did my high school in Concord, Massachusetts. And then my career in computer science actually started when I moved to Davidson in North Carolina, where I did some research on gender perception and differences in gender perception in virtual reality. And then I also was a tutor and a grader there. And then after getting some nice research experience at Davidson and figuring out, oh, this research thing is pretty cool, I decided to go on to do a PhD at the University of Maryland, where I studied locomotion and walking in VR. And I was a TA for almost all of the semesters while I was there, or a co-instructor for classes. And I mentored 4 undergrads who most of them are now off doing their own PhDs. And along the way, I did a couple of internships at Meta and NVIDIA, where I was looking at applied human vision for computer graphics. And this photo here on the top right actually comes from something towards the end of my PhD, where actually was a nice little bow to end off the PhD, which was I actually got interviewed by a kids science magazine. So as someone who grew up reading science magazines as a kid and who has some interest in like public communication of science, this was an awesome box to check off of my bucket list. And I didn't even know this was an item on my bucket list to begin with until I reached out. So that was a cool way to end my PhD. And then now I'm over at NYU, where I'm a faculty fellow. I'm doing more research on applied perception for computer graphics more broadly, so not just in VR headsets anymore. And last semester, I taught data visualization, and this semester, I'm teaching intro programming for mostly first-year students. And I'm mentoring students at all levels, at all degree levels. So that's a bit of who I am as a person. And now I can jump into the research that I do. So I'm, broadly speaking, interested in computer graphics. And more particularly, I'm interested in understanding how people use these computer graphic systems. And when we show them certain things on a display, how might they react to it? Are they able to tell what we're showing them on the display? Can they make out the different elements of whatever we're showing them? And how might that help them or hinder them in trying to do whatever they're trying to do with that computer graphic system? And so there's a highlight or a focus there on interactive systems. Okay, and so that shows up in 3 main areas where I study this sort of question. First is virtual and augmented reality. What you see here is someone walking a dog in VR and then walking a robot in the real world. And then another place where it comes up is in social computing. So how can we make computer graphics technology better for people who want to communicate with others in remote settings? And then the third area where I study this perception for graphics is in image and video quality. So it turns out there's a couple different communities that have a vested interest in figuring out can people tell whether or not this image we're showing you is good quality or real or fake? And so I'm studying how people come to those conclusions in computer graphics. And in order to do all of this, I actually end up drawing from a lot of different areas to come up with new solutions that maybe people haven't quite thought of yet, or coming at these problems from new perspectives. And so in particular, I tend to draw upon ideas from visual perception, from robotics, from computational geometry, and from statistical modeling. And so what I hope to show you today when I talk about my research is to show you how all these different areas can come together and how you can use these different tools in order to come up with new interesting solutions for some of these computer graphic systems. And I'll talk about two projects in particular, one on virtual and augmented reality, and then another on social computing. Okay, so let's jump right in. And I guess if anyone has questions at any point, just shout and I will do my best to answer. Okay, so first, what is VR? Virtual reality is when it's an experience where the user is placed into a computer-generated virtual environment, and usually their motions are tracked. So as the person moves around in the real world, the perspective in which they're viewing the virtual world also updates. And this is actually a key component of what makes VR feel interesting and makes people feel immersed in that virtual environment and makes it really feel like they're actually in that virtual world. It's because we have this high refresh rate, very accurate motion tracking. So you update your perspective and you're able to actually interact with that virtual environment. So you might pick up objects in the virtual world and they might respond like they do in normal physics in the real world. And this really helps to make people feel like they're actually in that virtual world. VR has all sorts of interesting applications to different domains. Entertainment, of course, is a big one, gaming, but then also socialization, connecting people across different distances, and then healthcare industry, mental and physical therapy. Job training is another one, so high-risk jobs where it's maybe not the best idea to get new people who are new to the job out in the field because it's dangerous since they're new. And so virtual reality is an interesting potential solution for that. And so a key component of all of these different applications of VR is that they're interactive. And so remember, that's what makes VR interesting, is the interactivity. And so a core component of that interaction is the ability to explore your virtual environment. So how do you move around? How do you get around to different locations in VR? And this is the focus of what my PhD was on. And so in order to illustrate why this is an interesting problem, I'm going to walk you through this situation here. So we have a virtual world on the left, and then we have the physical world on the right, and we have a user who's in VR. And let's say they want to walk on this path down here in the virtual world and want to walk down this virtual hallway along this green path. In the virtual world, that's fine. They could just walk in a straight line. But in the real world, they'd have to walk on that same straight line, assuming we're using natural locomotion. And that's a problem because there's this cabinet in the way that the user can't see because they're wearing this VR headset. And this is a fundamental problem with VR, which is that an unobstructed path in the virtual world could correspond to an obstructed path in the physical world, and the user has no way of knowing. And so they could hurt themselves. So the way, and researchers have come up with all sorts of solutions to try to mitigate this problem, and I'll talk about one such solution. But first, I'd also like to mention, what do current solutions look like out on the market? So we have these companies that are building headsets, and they have to come up with a way to solve this problem so that their users are not in risk of getting hurt. And so what they do is they have users fill out or specify essentially a play area where once you set up your headset, you say, okay, I'm only going to use the VR headset in this specified domain here, like this little blue box. And anything outside of that, the VR headset essentially doesn't work. The system, these manufacturers, they essentially turn off the screen and say, hey, you're about to walk out of your designated play area. That's a safety risk. Please turn around and go back into the center of your safe area and continue using your VR system. And this is not an ideal situation or a solution because they introduce these sorts of barriers here. Like you can see this red tape essentially that pops up in your experience. It happens in any experience, and it really pulls you out of that virtual environment that you were in. And so it's really annoying because you constantly have to reorient yourself and pause your virtual experience. So if possible, we'd like to get rid of this solution completely. And so I'll talk about one solution that tries to do this, but in order to explain how it works, I had to take a little detour and talk to you guys about self-motion perception. So when you move around in the environment, your brain is trying to figure out something about how you're oriented in that space and how you're moving through that world. And it's useful, your brain needs to know this so that you can figure out if you're on the right track, going to the right destination. And I will bucket, your brain comes up with information from all sorts of different areas to come to some conclusion about how you're moving. And I'll divide them into two categories, visual and non-visual. So your visual stimuli that are used to figure out how you're moving would be things like what's called optic flow. So essentially just the pattern of motion that you see as you move around or as objects around you move. And so if you see a very uniform pattern of motion across your whole visual field, that's a strong signal that probably you are moving rather than every other object is moving in unison. And then the other place where your brain gets information about how you're moving is through all the non-visual stimuli. So this would be things like your vestibular sense, which tells you something about how you're oriented. So this is your inner ear. That fluid in your inner ear tells you how you're oriented in the world and might contribute to you getting dizzy or something. And then another thing called proprioception, which tells you about how your body is positioned even when you can't see your body. So that's what tells you that's the system that tells you if your arms are in front of you versus behind you, for example, even if your eyes are closed. And there are some others as well that contribute to self-motion perception, but these are the main categories. And so there are two situations here that are interesting. So first is when the story that's coming from your visual information and your non-visual information, when they agree and they say the same thing about how you're moving through that world. In this situation, this is the normal situation when we move through the world. In real life, this happens most of the time. And so in this case, your brain is happy. It's able to come up with some cohesive story about how you're moving through the world, and everything makes sense. And then the other situation is where those two don't agree, and your visual information tells you one thing about how you're moving through the world, and then your non-visual information tells you another thing about how you're moving through the world. And in this case, your brain it can have some difficulty in figuring out how you're moving through the world. And this is actually what we believe to be the main cause for like motion sickness, for example. So if you think about being in the car, your body's stationary, but if you look out the window, there's tons of motion on the side from out the window. And so that can confuse your brain and it can make people feel sick. And so usually in this situation, when the two don't agree, we see a phenomenon known as visual dominance, which is where your brain tends to essentially just believe what it's seeing rather than what it's feeling. So you place more importance weights on your visual information for determining how you're moving through that world as compared to your non-visual information. And as a quick aside, if you're maybe curious why that might be the case, well, this is not a perfect explanation, but visual information is essentially just very information dense. So it would make sense that you can parse it very quickly and get a lot of information about your surroundings from that. And so there's actually lots of neurological evidence that your brain devotes more resources to visual processing over other information channels. And so this is a bit of an explanation for why this even exists in the first place. Okay, so that's how the brain figures out how you're moving through the world. And we can use this to help people move around in VR. We can take advantage of this inconsistency here. So this phenomenon of visual dominance. So there's this technique called redirected walking, which is a natural locomotion technique for VR. And so what you're seeing here on the left, this is a perspective of someone walking down a hallway in VR. They're just walking down a straight line hallway. And as far as we can tell, it looks like, yes, they're just walking in a straight line down this hallway. And then if I show you a bird's eye view of what's going on here, this is the top-down view of that virtual environment. This little white icon here, that's the user's position. And then what's happening is as the user walks, we're slowly rotating the entire virtual world around their position. And does anyone have a guess as to what this might mean, what implications this has for the user's physical trajectory? Yeah.
They're in a circle.
Yeah, they start walking in a circle. And so we can see that here. This user starts walking on a curved trajectory. And importantly, because we do these rotations slowly, they don't consciously perceive that it's happening. And so it doesn't interfere with their virtual experience, but we're able to help steer them away from objects that they might not be able to see that they normally would have collided with in the physical world. So if you imagine maybe an object here, they've now successfully avoided it. And so a core problem with redirected walking is figuring out how to apply this technique to help people avoid as many collisions as possible. So since I'm going to show a lot of diagrams, I'll just give a couple of definitions and ground rules so you understand the following slides. So in VR with redirected walking, we have the physical world and a virtual world, which I'll represent with these sorts of shapes. These are the boundaries. And then we have black shapes here, which represent obstacles. And then we have the user located in both environments at the same time. And they want to travel on some virtual path. And now that we know redirection exists, we can manipulate this virtual path in the corresponding physical world and steer them on different physical paths. So for example, we could steer them to the right here on this first path, or we could steer them to the left here on this second path. And then the core question is, which of these paths is the optimal direction to steer the user? And so in this case, of course, this second path is the one we prefer because it steers them away from this obstacle here in the physical space. But this is an oversimplification. And actually, in fact, for any given virtual path, it's not just two physical paths that we could steer the user along. And we have an entire range of infinite possible paths that we could steer the user on. And so this search space for this problem of trying to find the optimal path is actually infinite. And that's, of course, computationally intractable. So a lot of my research in my PhD was figuring out how can we make this problem easier to solve. And in order to do that, I built upon a key observation, which I'll walk through now and help you hopefully come to the conclusion yourself as well. So again, consider this pair of environments, physical and virtual. The user wants to walk forward in VR, but they can't because there's an obstacle in their way. It's the same locomotion problem I described earlier. Okay, so now consider this new pair of environments. We have the physical on the left and the virtual on the right. And let's say the user wants to travel on this path here. They want to walk forward and then take a right turn and continue walking forward. So I invite you to now take, I don't know, 30 seconds or so, talk to your neighbors if you want, maybe draw things out if you have a piece of paper handy, and try to figure out which of these three options for starting locations in the physical world, A, B, or C, would be an optimal choice to place the user in to avoid collisions, or as many collisions as you might think possible. So take a couple seconds, talk to your neighbor, and you can rank them as well. Maybe multiple options are good. Which ones might be better? Yeah, so let's assume they're all facing north, just for simplicity. In each case, you face to the north. So in the interest of time, I'll just keep going because I don't want us to spend too long. But I guess, does anyone have an idea what they think the best option would be? You can just shout it out. B. Okay, I like that option. I'm going to walk through them in order from worst to best. So the worst one is option C. So if you place the user at starting position C, and then if we copy paste essentially that path, we can see that it's not going to work out. The user will walk right into a wall. Okay, what about option B? I like this option. It's a pretty good one. So we put the user at position B, and then we draw that same path. The user is able to travel on it with no collisions. So things seem all right for position B, but I will note that you might also want to notice that the virtual world, once they finish this trajectory or this path, they're in a big open space in VR. And now in the physical world, for position B, they're left standing in the corner. And so that might lead to problems later. But at least for this path that we have here, B is perfectly fine. And then option A, I think is the best one. So we can place the user at position B, or sorry, position A, and we can actually also apply some redirection to their path. And then we can have the user be placed sort of in the center of this physical space in this wide open area. And that matches the structure of this virtual environment pretty nicely. And so whatever the user might want to do after they travel on this path, probably there's a decent chance, at least better than the other two options, that they can do that and walk on that path without any collisions. And so this highlights the key observation we made that I built a lot of my PhD research on, which is that environments can be globally dissimilar, which, as I've told you so far, leads to collisions in VR, but they can have regions of local similarity, and that these regions of local similarity can actually lead to collision-free navigation. So I'll show it here one more time. Consider this pair of environments. They're dissimilar on a global scale, but if the user walks straight forward in a straight line here, because of local similarity between the two environments in terms of the structure around the user is able to walk on this path freely with no problems. So this tells us we need to wait, if we want to build an algorithm to take advantage of this, we need a way to summarize the structure of the environment. And to do that, I borrow a technique called visibility polygons from motion planning and computational geometry. So if you have a polygon in the plane and a query point, the visibility polygon is this region in blue. It's essentially all the points in the polygon or in the plane that you can see if you were to stand at that position. And that's how we use it in our redirected walking algorithm. So consider this pair of environments. The user tries to walk forward and they can't because of collision. And another thing that's tricky about redirected walking as a problem to solve is that identifying these collisions is a little hard unless I show you what path the user travels on, right? Unless you know something about where the user is going to go, it can be hard to figure out what's the optimal steering direction because that depends in part where they want to go. And so we realized that actually with visibility polygons, we can sort of circumvent this problem, at least a little bit, doing the following. So if we draw or compute the visibility polygon for the user's position in the physical and virtual worlds, we overlay them on top of each other. And if I draw that same path the user tried to walk on, we can see that the collision happens exactly on this boundary here. And this boundary is defined as the region where the user remains inside of the virtual visibility polygon, so the pink polygon or red, and they exit the physical polygon in blue. And so we can see that actually all along this edge would be different collisions. And then also down here on this edge would also lead to collisions in VR navigation. And so we can identify, actually, if we just turn the user around a little bit to their left, so they're now facing to the west, and then we update the orientation of that physical polygon, and then I draw that same path again, we can see that that path lies entirely within both of these physical and virtual polygons. And indeed, when the user walks forward along that trajectory, they're able to do so with no problems. And so using this observation, we built an algorithm that takes advantage of this to steer the user more optimally without knowing explicitly where they're going to walk. And so how it works is on every step, on every frame of our simulation, we compute the visibility polygon for the physical and virtual worlds for the user's position. We cut it up into these little slices. We figure out which slice in the virtual environment is the user walking towards, which we call the active slice here. I've shown it in yellow. And then since we care about local similarity leads to collision avoidance or higher chance of collision avoidance. The next step is to figure out which slice in the physical polygon is most similar in structure to this active slice in the virtual world. And for our work, since we wanted to keep things simple, to see if simple would work, which it does, we just used area as a measure of similarity. So which of these slices has a similar area to this active slice in VR? And in this case, that would be this one here. And then the final step is we apply redirected walking to steer the user towards the center of this triangle or this slice and away from whatever direction they were currently walking in. And we just do this on loop every single frame. That looks a little bit like this. This is a simulation because this study was done during COVID, so we weren't allowed to run user studies. And this is a visualization of what it looks like. And you can see, you might be able to see every time the user gets too close to an object, they have to stop and they do a little spin. And that's to simulate the fail cases where redirection can't keep you safe, where we have to initiate what's called a reset, where you prompt the user to stop walking, turn around, and then once they're now facing away from whatever object they were about to walk into, then they're free to continue walking. And so once those resets happen, you can see that the virtual world, the person stops walking because the virtual experience is paused. Okay, and so to evaluate this algorithm, we had a benchmark, a set of benchmark environments, 4 different pairs of environments, physical and virtual, and one of them had moving objects in it as well. And we compared how well people can avoid collisions or these resets with our algorithm compared to some of the other state-of-the-art algorithms that people were using at that time. And the results look something like this. So y-axis is number of resets here, and lower is better. We want as few of these interruptions and collisions as possible. And so our algorithm here is all the way on the far right, highlighted with these boxes. And we can see that indeed we had statistically significantly fewer number of resets or these near collisions with our algorithm compared to the other algorithms. And so that's a win for our algorithm and a win for the notion of local similarity for collision avoidance. So some key takeaways from this work I'd like to highlight. First is that shortcomings or maybe idiosyncrasies in human vision can enable new methods for VR locomotion. And that local similarity between your physical and your virtual environments is useful for collision avoidance. And that reformulating a long-standing problem, this VR navigation problem, reformulating it in a different way can make it easier to solve in some ways. So for example, we used motion planning techniques to help steer the user around and avoid collisions, which is something that roboticists have been doing for like 50+ years. And then we also used computational geometry as a new language to build some new analysis tools that enabled us to design new algorithms. So that was the first part of my research, where we studied how people navigate in VR and tried to optimize the graphics renderings to make people safer. And now I'm going to shift gears a little bit and talk about teleconferencing systems. So this was some work done in collaboration with NVIDIA at an internship. And so here's a picture of people on Zoom. We're all familiar with this at this point. Probably some people are seeing it right now on the Zoom call. And this is okay. It sort of gets the job done for what you need to do, which is talk to people. But it has a lot of problems with it because there are lots of various missing or degraded or completely missing social cues. So things like latency, if people have bad internet, it can cause problems. Maybe there's no eye contact that's possible. Or there's bad audio mixing, so it's hard to hear some people and other people are way too loud. Or people have low resolution cameras, or they completely turn their camera off, so you can't even make out facial expressions to figure out, do people, was your joke funny or not, even if their microphone is muted. And in particular, I want to talk about this eye contact issue and telling where people are looking. So Just to really spell it out, this is the problem. So in VR or in Zoom settings, you're looking at your monitor and you have your camera usually mounted on the top of your monitor. And so if you're speaking and you want to see what people are doing in your Zoom call, you need to look at your monitor, like this guy is on the left. But on the other end, you're going to show up to the other people on their Zoom screens as something like this, where it looks like you're kind of looking down a bit, because relative to the camera, you are, because the camera is mounted above the monitor. And so if you want other people on the other end to feel like you're making eye contact with them, you instead have to look directly at the camera, which is not at the same location as your screen. And so this can be weird for you now, because you can't tell what people are doing on Zoom. And you can't pick up on whatever social cues, nonverbal cues they might be conveying to you. And so this is one of the problems with things like Zoom and FaceTime. And so computer graphics researchers and engineers have come up with all sorts of different solutions to try to mitigate this and reintroduce the ability to make eye contact and tell where people are moving. So on the top left here, this is from NVIDIA. They essentially just redraw your eyes, your pupils, so that it looks like you're looking at the monitor or the camera, sorry. On the top right here, they have a bunch of 3D displays and they have a bunch of multiple cameras set up at different angles and different positions around the user so that they can create a 3D reconstruction of each person at each station. And then they reconstruct you and project you on these 3D displays so that you can get a lot of cues about people's directions of their body orientation, and you get depth cues and all that. And then on the bottom here, this is a Google's version. Oh, the video stops working. That's Google's version on the bottom, which is essentially just like a more productized version of the same thing. And so all these graphic solutions, they are pretty expensive, right? You need to enable, or you need to use a lot of compute resources in order to reintroduce some of these social cues. And so it begs the question, like, how worth it is it? Because, do I really want to buy a 3D display and 7 cameras just so that people can tell which direction I'm looking? How important is it? How much better is it going to make my experience? So that's a natural question you might ask for these sorts of graphic solutions. And so that's what we tried to set out to make some progress on answering with this project with NVIDIA. And so the way we did that, the way we tried to answer this was by measuring people's performance at a proxy task. So in our case, we were trying to measure not how important these social cues are for your experience, but instead, we were trying to measure how well can people detect these social cues that show up in these situations. And the argument here, or the line of reasoning here, is if this social cue is really hard to detect and people are really bad at detecting a particular social cue, that suggests that it's probably not very important for your social experience, because we're social beings. We've evolved to work together and collaborate with people. And so our brains have come up with lots of specialized pathways in order to pick up on various social cues very well and very efficiently. And so if you're bad at a particular detecting a particular social cue, that would suggest that it's probably not very important for your survival and for your socialization. And on the flip side, if you are very good at picking up on a social cue, that suggests it's probably useful for you in some way. So I'll give a demo of that here. When you look at these 2 photos of a person, can you tell which one is looking at the camera and which one is looking a little off to the side? If anyone thinks they know, just say it. Yeah, Michelle. You think the right one is looking at the off to the side? Yes, that's correct. The left person is looking directly at the camera, and on the right, they're actually only looking about 6 degrees off away from the camera. And so, people are all sitting at different distances from the screen right now, and so this face is showing up at different quality on your retina, and everyone's able to tell probably that this person on the left was looking at the camera. And so this suggests, hey, this is actually something people are pretty good at. And so there's actually a lot of work that has studied this direct eye contact case, where when you're looking at another person, how can I tell, or how well can I tell if someone is looking directly at me? But there's comparatively a lot less work looking at studying how well you can tell where another person in the room is looking. So we have a bunch of people in this room right here. And so when you look at me, you can tell whether or not I'm looking at you as I speak. But not many people have actually measured how accurately can people do that task. And so that's what we set out to do. And we use images like this, which are meant to simulate what we think these sorts of graphic solutions for video conferencing might look like in the future. So you have people in a shared space rather than showing up as panels on a window on your computer. And you have like full body avatars. And so the task we had users do was figure out which avatar is the viewer looking at. So the viewer was indicated with this red arrow here. We call it the cued avatar, or the viewer. And the task for our participants was just showing a bunch of images like this with the cued avatar, report who at the table this avatar is looking at. And so in this case, that would be this person on the left here. And I can actually show you what this experiment looked like for the users. So They just did this hundreds of times in a row, essentially. So we showed them the images for only a fraction of a second, and they reported which other avatar at the table they thought the queued avatar was looking at. And even though we only showed it for a fraction of a second, it turns out that, as you'll see soon enough, this was actually not, it wasn't like too short of a time if people were actually able to do the task. So this is what we had people do in a bunch of different situations. You might have noticed the images sort of change. And so we had 3 scene conditions that we looked at. The first was unnatural poses in a rich scene. So what we mean by unnatural pose is that the orientations of people's torsos, heads, and eyes did not follow natural statistics of how people move those body parts when they want to look at things. And instead, torsos always face the center of the room or the table. And these avatars only rotated their head the full amount of degrees needed to look at the target, and their eyes always looked straight forward in the direction of the head. And this is very unnatural, right? This person's totally craning their neck all the way to the side just to see this person. And then rich scene refers to the amount of visual detail we have in the scene. So you can see there's like glyphs and patterns on people's shirts to tell you something about where the torsos might be facing. And there's all these details in the background on the wallpaper to show you this brick texture, which tells you something about the structure of the environment. So this helps give some 3D cues about the structure of the environment, but it can also introduce what's called visual clutter, which is essentially, this is a short explanation, but essentially when there's lots of details and small elements in your visual field, especially in your periphery, it can make it very difficult to make out individual elements, and things sort of get jumbled together. So that was the first condition. We also studied natural poses in a rich scene. So now people's torsos, heads, and eyes rotated the correct amounts as they do in natural statistics when real people are looking at objects in different orientations. And we still had the rich scene, so there was still lots of details and visual cues about the structure of the scene. And then the third condition was natural poses, but now we had a sparse scene. So we removed a lot of the details that might provide you cues about where people are orienting. So the glyphs on their shirts are gone, and a lot of the texture from the background has been removed. And we showed people images from all these different conditions and had them do that task I showed you just a second ago. And in order to measure how well people did this task, I need to walk you through our performance metric that we computed. So let's consider this diagram here. This is like a top-down bird's eye view of those people sitting at the table, those 5 avatars. And the camera would be somewhere down here to render the screen or to render the image. And let's label them, these avatars, for the sake of reference and explanation, 0 through 4. And let's only consider avatars 0 and avatar 2. And let's say that avatar 0 is the queued avatar. So the task is to figure out who at the table avatar 0 is looking at. And in this case, that would be avatar number 2. This black vector here, that's the ground truth vector of where the user or the avatar is looking. And let's say for our experiment, we showed people this setup, and everyone got the answer right. So everyone reported that the target in this situation was avatar 2. So if we plotted all of the responses, we would get a histogram that looks something like this, where every response is centered on avatar 2. And then if we fit a distribution to those responses, that's indicated by this vertical green line here, which is essentially just a completely straight line that always returns 2. Okay, but now let's say a couple of people got the answer wrong. And so some people said that avatar 1 was the target. So now the distribution of responses looks something like this, where it's now changed a bit. And if we fit a distribution, a PDF, a probability density function, to the responses, we get something like this. So now our distribution has some width to it, and the peak lies somewhere between avatars 1 and 2. And then let's say even more people got it wrong. The peak has now shifted even further towards avatar number 1. And so this is from this distribution, we can compute that performance metric, which we call gaze direction estimation bias. And so if we draw back the ground truth vector here, and then we compute the angle between the ground truth vector and this average of all the responses, this angle right here, that's theta, which is actually the same as the mean of this peak, or sorry, the mean of this distribution, which is the peak of the distribution here. And so this angle, theta, tells us something about, on average, how far in either direction, left or right of the target, do people tend to view the avatars as looking. So essentially, what's their inherent bias in how accurately they can do this task. And then a secondary metric that we use is the standard deviation of this metric, which tells you something about how precisely they can report this. So what's the spread, and how often, if you show them the same image over and over again, how often will they report exactly an avatar aligned with this bias vector. And so these were the, oh, question, yeah.
Is this affected by the direction in which the other people?
So for Zoom people who maybe didn't hear, the question was, is this measure affected by the direction in which other people are looking? So the other avatars at the table. I did some preliminary look into that with the data that we collected. And it looks like the answer is no, which was a little bit surprising because you might think, you know, if everyone's looking in a particular direction, you may also tend to look in that direction and it might bias you to think everyone's looking in the same direction. That answer of no that I just gave is not a perfect answer though, because our experiment was not set up to specifically study that. And so it turns out that the conditions for the number of images where the number of people were looking at a particular target was balanced or was not balanced. And so, you know, the numbers don't work out quite so well to do proper statistics, but from what we looked at, it didn't seem to have an effect, but it's definitely an open question.
I was also thinking about number one, looking at the person with the arrow. So I think it might be possibly.
Yeah, exactly. Yes, that's also very true. I think it's probably pretty reasonable and likely, actually, but with the setup we did, that wasn't our main research question, so we didn't have perfect data to accurately answer that. Okay, and so this is what the results look like, something like this. So again, top-down view, and it's maybe a little hard to see. What I'm plotting here is the average bias vector for each of the different conditions. We had both long and short displays for the images, so we gave them infinite time or we showed it for a fraction of a second. That's why there's so many of these different results. And what we can see for most conditions in terms of avatar configurations between the viewer and the target, in most of the cases, people had a bias to perceiving the target or the viewer as looking further away from the camera than they actually were. So if you imagine the camera, again, as being down here somewhere in a top-down view, we can see that all of the bias vectors for this pair 0 and 2 are behind the avatar. And so this means that people perceived, for some reason, they were biased to perceive that the avatar, the viewer, was looking further away or was turned further away from the camera than they actually were. And then if I plot those same results for two of the conditions, the viewer and target conditions, along with the standard deviation of their responses, we get something like this. So in the left plot here, we can see, again, there's a consistent negative bias or maybe not too much bias for this viewer target pair. And then in this other viewer target pair where the viewer is number 1 and the target is number 0, there's actually a positive bias. And this was like pretty much the only condition where that positive bias was consistent. And then we can see that their accuracy is roughly in the 10 to 15 degree range across all these conditions. And that was pretty consistent. Okay, and so the key takeaways from this that I'd like to leave you with, if you don't remember anything else, is that computer graphics innovations can help make teleconferencing better and feel more natural through new advancements to things like high resolution 3D displays, AI animated avatars, and spatialized audio. And then I'd also like to highlight that humans are very good at picking up on these social cues and incorrect social cues especially. And so the bar is quite high for realistic telepresence. So if you want to implement one of these systems, the bar to avoid the uncanny valley is pretty high. And then an understanding of the accuracy for social cue perception, I think, is useful as a clear benchmark for graphics engineers to understand how good do they need their systems to be. So actually, since this was an internship, at the end of the internship, we were able to say to a sister team that was working on implementing these systems, we were like, hey, here are the numbers for how accurately people can judge where another person is looking in these displays. And by the way, they seem to have this kind of weird bias to be biased to perceive things away from the camera or people away from the camera. And so now the graphics engineers and researchers can take this knowledge and try to come up with a display system that takes these into account and tries to avoid uncanny valley situations as much as possible. Okay, and so with that, those are the two projects. Oh, question, yes.
Okay.
Yeah.
Did you persist throughout the entire experiment, or was that primarily driven by the end of the experiment where the users may have been under adaptation?
So repeating for people who may have not heard on Zoom, the question was this bias that we see, did it persist throughout the entire experiment, or was it only shown or dominated maybe at the end of the experiment where people have adapted to the stimulus? I don't know the answer to that yet. So that's currently, we're writing up the manuscript now and we're doing a lot of the analysis. There's like tons of data, so I'm working through it in a lot of different ways. And there's eye tracking data paired with it. So we have tons of different ways that we need to kind of figure out what we want to do with the data at this point. And so I don't have the answer to that question. My guess is no, but at this point, that's kind of just a hunch. Another question?
What display was this done with? Was it a stereo display?
Yeah, so the question was, what display was this done with? It was just a regular computer monitor. It was well, the size doesn't matter. It was 40 degrees of your visual angle, horizontal, and it was just a regular computer monitor, 1080p.
You think you get different results if it was done with stereoscopic display?
I think yes, you probably would get different results if it was done with a 3D display because they have extra cues to figure out the 3D structure and depth cues and all that. So I think you probably would get better results in terms of people would be more accurate at telling where people were looking or the avatars were looking. I don't know how much better it would get, but my guess is it would be better. Yeah. Another question?
So in the physical world, you talked about that we're good at telling if you're looking, I'm good at telling if you're looking at me, but you didn't talk about if I'm good at telling in the physical world, which one of these people you're looking at. So is there a good benchmark for the physical space on this question, or is this an open question even in the physical space?
That's also, as far as I'm aware, a pretty open question. Nobody's really studied it. I'm not too sure why. I guess I don't know. Now we have a driving application or use case to maybe make people want to study it. But as far as I'm aware, it's not been very well studied for the real world either. Any other questions? All right. And if not, then I can wrap up a bit and talk about future work and what I'd like to do moving forward. So again, going back to my research overview, these are the types of problems I like to work on. Applied perception for making computer graphics better and making the user experience better. And my 3 areas that I like to focus on are VR, AR, social computing, and image and video quality. And so focusing on AR, VR first, I'm interested in what could be described as active vision or perception for action. So how do people do tasks in these complex virtual environments where you have lots of rich visual stimuli and people have complex tasks that they want to do. So one example of such a task would be locomotion. So how is gaze control paired with your foot control when you're trying to walk through an environment and navigate through maybe complex environments, and how might that change? So what you're seeing here, this is for the real world, but how might that change when you put people in VR, where actually usually your floor is completely flat, but what you're seeing in virtual reality might be an uneven floor. So I'm interested in that. And then also for fine manipulation tasks with your hands, so things like maybe sculpting. How do people control their gaze when they're doing these manipulation tasks, and how does that interact with their ability to do the manipulation task, the smoothness of their motions, those sorts of things? Because these optical displays or these virtual reality displays have all sorts of optical problems that come with them. And so it's a question of how much might that get in the way of you doing those fine-grained tasks. And some downstream applications that would motivate these sorts of research questions would be things like job training, so manufacturing maybe, or artists who want to train with and don't want to buy a bunch of clay to do sculpting. Healthcare applications for things like rehabilitation for people with motor disabilities or surgery training, and entertainment, of course, like immersive gaming and sports, VR sports, things like that. And the other area I'm interested in working more on is social computing. So the question here is, how does the avatar appearance affect your social experience with that avatar? And so one example of a place where I'd like to study that is with the effects of body shape and skin appearance on your ability to pick up on social cues. So unfortunately, computer graphics has some algorithmic biases baked into the way we render skin, for example, and how we compute how light interacts with objects to make a final appearance, or in our reconstruction algorithms that maybe are not able to reconstruct people of different body shapes all to an equally accurate fidelity. And so I'm interested in when you get these sorts of things wrong, as many of these display systems currently do, unfortunately, how might that affect your social experience when you're interacting with these virtual agents? And then for VR settings, immersive VR settings, when you have like a headset on, how might facial animations and the fidelity of those, as well as other body animations like your hands, how might that affect your social experience when either talking to other avatars or when you see yourself moving in VR? Does it feel like what you're doing, your virtual avatar is doing? Does that feel like what you're actually doing in the real world? Those sorts of questions. And so downstream applications here would be in like telehealth or remote therapy, for example, or education. If you could make Zoom better, for example, during COVID, I'm sure everyone would have appreciated that. And then in business as well. And then finally, image and video quality. I didn't get to talk much about this, but here I'm interested in when you show people videos and images, how can they tell whether or not there's artifacts? Can they tell that something is wrong with the image that they're seeing? And 2 example areas where I'm interested in this, one is deepfakes, or I guess more generally AI generated images. So we're seeing this blowing up all over the place now. all sorts of AI generated videos and images popping up everywhere. And the question might be that you might ask yourself is this image even real, or was it generated by an AI? And these AIs are not perfect, so they tend to get things wrong. Maybe they draw too many fingers on the humans, on the hands, things like that. And so a question there I'm interested in studying is which of these visual features stand out the most to people and maybe are used as a cue that, oh, something is off here, and maybe attract your attention as you look at these videos and images. And can that be a signal for whether or not people think that this image is AI generated or not? And then another place where this is interesting, it turns out that the people who do video encoding and streaming, they need to compress these videos so that they don't use a whole bunch of bandwidth. And so you can stream your Netflix in real time and don't have to wait for it to buffer. And so they have a vested interest in understanding when I stream or compress my video and then decode it on the other end, are artifacts going to show up? And if they are going to show up, how visible will those artifacts be for people? And so what we're studying there, a lot of work has been done on the metrics side to come up with image metrics to judge quality or to rate quality, but there's not much been studied in terms of how do people actually look at these images? What sort of gaze strategies do people use when you show them these corrupted videos? And how do they try to find these corrupted artifacts when you show them videos, when they know that maybe an artifact does exist? So those are two areas I'm interested in. And then the downstream applications here that motivate these research questions would be things like content delivery, so compression and streaming, content authentication, deepfakes detection, digital forensics, things like that. And then entertainment, so gaming, we want to render video games at high resolution in real time, and then also like VFX rendering. Okay, and with that, here are the references for all the different images and papers I referenced throughout the talk. And I would like to say for any students who are in the audience, if you liked the sections where I talked about perception of like optic flow or the social perception, I encourage you to check out classes in perceptual psychology and social psychology. And for any students who liked the parts of the talk where I talked about like motion analysis, trajectory optimization, and geometry for describing your environments, I encourage you to check out classes in robotics and computational geometry to learn more about those. And with that, I thank you so much for your attention, and I'm happy to take any questions you might have. Steve?
So I really like the stuff that you're doing, especially with the book and computation. But you're computing that as basically the anti-umbra of a point light source.
Yep.
And people are in point light sources.
Yes.
They are wide and deep, where the width is maybe more important. If you think about doing it with the anti-umbra of a line light source.
Okay, I have not thought about that. I'll repeat for Zoom. The question was, we compute these visibility polygons with a point source, essentially. And the question was, people are not points. So have I considered computing these polygons, these visibility polygons with a line that would represent the width of these people instead? I have not thought about that. It's probably, I think it definitely would be better because it's just a more accurate representation of the person. I don't know how much better it would be in terms of like, is it worth it? I don't know how much more expensive the computation is. Probably not that expensive. Yeah.
Expensive, and that would also let you know if there's a narrow passage ahead.
Yes.
Right.
Right.
You were going to get through it.
Right.
With a physical passage.
Yeah. So I think it probably would be worth it in that sense. And yeah, I don't know. It's a good idea. I haven't done it, but it probably wouldn't be that hard to implement and see how much it helps. I like that idea though. Thanks. Yeah. Any other questions? Yeah.
You said for this project, the project on the right, that you had done it during COVID. So
Yes.
for looking at virtual simulations, have you done physical?
So this work on designing algorithms to optimize collision avoidance, I kind of got bored of that a little bit by the time COVID ended, and I was focusing on other parts. When COVID did end though, I did start putting people in headsets and having them move around with redirection. But I was looking at other research questions rather than trajectory
Yeah, 'cause I
optimization.
can imagine a lot of those issues would come up in like that. Well,
Yeah,
yeah.
right. And like that area is a little saturated, the algorithm design world. So I wanted to focus on some other questions within it.
This
Yes.
question may have the same answer, but in that same work, you looked at moving obstacles in the virtual space.
Yes.
Did you look at moving obstacles in the physical space?
I did not. That's initially how I wanted to study it. That was what I wanted to study first. But it leads to problems where, so this notion of resetting where you have to pause what you're doing and turn around, that question actually becomes very complicated when the objects are moving, because normally when we tell people to stop walking to avoid a collision and turn around to avoid that object, since that object is stationary, we know exactly how much we want them to turn in order to avoid that collision. But when the objects are moving, you don't know where that object is going to end up. And so, maybe you don't, and if you don't have information about where the object is moving, it becomes really hard to know how to tell the user to move. So for example, if someone's just walking past you, all you would need to do is sort of pause what you're doing for a moment. You don't need to turn around. But let's say someone walks up to you and they don't move, or like a car parks in front of you and it's parked there for the next few hours, then you would want to tell the user to start turning around. And so I was trying to implement this actually, and then I realized this problem, and I think that opens a whole new can of worms. So I just opted for only virtual environments because it was more well-defined there. Another question?
You had said like when you have to do the reset, that's kind of like the failure case.
Yes.
Finding a possible path out
Yeah.
of collision avoidance. Was like when you're optimizing for that path, is the notion of reducing the amount of resets that you might have on a longer trajectory part of that optimization, or?
It depends on your method. So there are some methods that only consider, actually the vast majority of methods for this actually only consider like the near future or in this exact moment. And so what's the optimal direction to steer you just for this moment? But if you have information about the full path, then yes, you can do more long-term optimizations. That becomes more expensive, like computationally to compute. And then furthermore, you introduce the question of how accurate is that prediction of your future trajectory? And so, if your accuracy in that prediction is bad, then any optimization you do may not turn out to be that useful. And so people have tended to prefer to focus on the instantaneous case where, okay, if we freeze everything here and need to figure out the optimal direction to steer you, what's the best option? And actually my work here with these polygons was trying to sort of get around that, which we're kind of doing an implicit prediction here, actually, if you think about it. So when we compute these polygons, this is a description of the entire space around the user that they could feasibly walk in, at least for the next few seconds. And so by doing this sort of overlaying trick and figuring out optimizing the overlap between these polygons, we're implicitly actually doing a kind of prediction where we say, okay, the user is probably going to walk in this direction where there's open space. And so maybe we won't know the exact trajectory, but if we maximize this amount of overlap, it's probably going to work out for the better. But technically speaking, it still only works on a frame-by-frame basis. But by using the structure of the environment, we can sort of do an implicit prediction there and maybe optimize further.
Okay, so like maximizing your area is always just going to give you, I guess, more potential.
Yeah, essentially. Yeah, that's a good question. Any other questions in Zoom, maybe?
Can you hear me?
I can hear you, yes.
Oh, very interesting work. I have a question about the bias of the gaze estimation, the second piece of work you talked about. You said the bias is to be further away from the camera, right? Do you have any intuition on why that's the case?
Yeah, so just to repeat, the question was about why do we see this bias in that gaze perception experiment? Why is there a bias for people to perceive the avatars as looking further away from the camera? And I think, and is there intuition for that? I think it's not a slam dunk. This is definitely the answer, but I think the intuition is essentially, let me actually jump back to some of those images. So if you consider this person here on the far right, you can't see like any of their facial features at all. And I think this contributes to this bias, essentially a question of how much of their facial features can you see? It seems like, and if, for example, this woman here, a lot of her face is covered by her hair. And so when she's on the end and actually looks at her neighbor, you can see absolutely nothing of her face. And so I think the intuition for why we see this bias is that because people can see less of the facial features, for some reason that causes them to assume that you're looking further away or further in one direction than you actually are. And then, for example, if I go back to the results, we see the opposite of this, which is why I think this intuition is perhaps correct. Actually, I'll show it on this slide. So this situation, this one here, where the viewer is avatar number 1 and the target is avatar 0, we actually see a positive bias where we're biased to perceive them as looking towards the camera more. And so that's the opposite case here, where when you think about this avatar, looking at this target, we can actually see more of their face. And I think that's an explanation for why this bias exists. Thank you for the question. That's a good one.
Great, thank you.
Any other questions?
Can I ask a question? Sorry, I don't know how to raise the hand, so I have to speak.
Sure. Yeah, go ahead. I can hear you.
Okay, thanks, Niall. Very good work, very interesting work. I just want to have, I just have a high level question. You know, for all your work from like redirection control to gaze correction and image quality evaluation, it seems to me there has been so many works in each of these areas, like the, you know, the redirection control. As far as I know, SIGGRAPH and HCI community has studied that. And the gaze correction, in my memory, Microsoft has done that back to even early 2000. So I wonder, you know, as you are starting a new sort of career, right, in academia, what would be your unique philosophy or unique angle to tackle those relatively old, well-studied problem? Can you comment that on the high level?
Sure. So repeating for people, the question was, there seems to be actually a lot of prior work in a lot of these areas that I talked about today. And so moving forward, how do I plan to, I guess, do something new and fresh and come at it from a new angle, given that there's already so much work on it? And I think my answer to that is in the interdisciplinary nature of my work. So if I go back to this first slide here, really what I like to do, the types of problems I like to work on and the types of solutions I like to come up with are taking these longstanding problems that people have been working on for a while, and then trying to see, does it have any parallels to some other area where you maybe solve a similar sort of problem? Like in the case of VR and locomotion, it's the same as, it's very similar to motion planning for robotics, where you avoid collisions. And so then taking these ideas from other areas that have a lot of parallels, and then seeing, oh, can we maybe adapt the definitions or the techniques that are used in these other areas to come up with a novel solution in our domain of interest, in this case, like AR, VR. And so to your question, I think moving forward, my strategy, which is what I did like during my PhD as well, is just read a bunch of papers from a bunch of different areas that I just might find interesting. And what I found is that the more I read from a broad set of fields, the more you see all of these different problems that other people are working on, and you can see the similarities and the differences between your problems and their problems, and then you can pick up on their techniques and try to apply them to your domain. And oftentimes, from my experience at least, it leads to these sort of interesting solutions that lead to maybe better solutions or open the door for better solutions.
Thank you. Thank you.
Questions? Thank you very much. Join me in thanking the speaker, please.
Thank you.
Thank you.
Thanks. I can stop sharing now.